Pleasure today to receive Nathan Mayne. Nathan works at the University of Exeter in the UK. He's associate professor in the astrophysics group. So he worked here in Exeter for long years, but he worked on a lot of different subjects, on surface placement, polaritron, on radiative transfer, on brown dwarfs. And for several years, he works now with his group on the atmospheres of exoplanets, on the theory and from observations, exoplanets and brown dwarf. So the study of exoplanet atmosphere is studied for a few years now, including at IAP. And we know very well that team at Exeter, for example, David Singh, who was postdoc with us a few years ago, came to Exeter before leaving to the US. There are also other names that we know well at Exeter, as Isabelle Barra, Gilles Chabrier, and so on. And today, so we have Nathan Mayne, who will present a seminar with the title Exoplanetary Atmosphere in 3D Implication from Radiation-Chemistry-Hydrodynamics Simulation. So Nathan, please, I let you the floor.
Thank you very much. So yeah, thank you for inviting me. Obviously, I'd much rather be there in person, but this will have to suffice. So the talk, as Guillaume said, is about exoplanet atmospheres and in particular modeling, but I will start with a little bit about the observations. I know some of you are very experienced in that, but maybe others won't be. So the group at Exeter, really my group is a connection between the UK Met Office, focused on Earth's weather and climate, and the astrophysics department. There's some names here of really the people that do the work, the postdocs and PhD students that have been involved. And this session's recorded, so you can pick those names out and go back and see them. I've picked out some really key people here, James and Ian. They actually work at the UK Met Office, but they've been sort of seconded to come and work with me on this project. And Eric Hebrard, Pascal Trembon, Hugo Lambert, these are other people that really help me to keep this project going. Okay, so the idea is to, excuse me a second. Just get my pointer working, apologies. Oh, I forgot. So recently we've had some flux in the department. We have some postdocs that have moved on to various positions. Florian Debras has moved to a CNRS position, and a couple of the postdocs have moved to actually the UK Met Office. And we've had a new influx of postdocs who will come in and take over the projects. Okay, so to start with the exoplanet observations, we have obviously a raft of instruments, both on the ground and in space, aimed at detecting and characterizing. And I suppose many of you will know what's really exciting about exoplanets at the moment is that the next sort of 5, 10, or even 15 years, we will see a huge investment in observational facilities. Now, just very briefly, you probably are well aware that things like transits, which David Singh is an expert in, can give us the radius and orbital period of the planets just by observing the dips in light as the planet occults the star. We also have radial velocity detections, just detecting the Doppler shift in the stellar lines, the stellar spectral lines that give us access to mass and again, a confirmation of orbital period. And that's great. That gives us bulk properties of the planets, radius and mass, and therefore we can infer a density. But in order to really understand their climates and atmospheres, we have to go a bit further. So we need to understand the emission from the atmospheres themselves. The tool that probably is the future in this direction, although there's lots of technical work to be done, is direct imaging, where we can get the direct emission from the planets themselves by using a coronagraph on the central star. Microlensing is a sort of another detection technique many of you are probably aware of, but doesn't sort of relate to me in the sense that we can't characterize many of those targets. Okay, so the observations themselves have thrown up huge questions. It's clear that planets are very diverse, but the key ones that I'd like to focus on today, or that we've been working towards solving, is first of all the inflation of hot Jupiters. So we see here a graph of the irradiation that's received by a Jupiter-sized planet in a short period orbit against its radius. And this line is sort of a fit to the observed radii, and it shows you that as the irradiation increases, the radii of the planet increases. And this is beyond the predictions of the fundamental theory, the balance of kind of Coulomb pressure and electron degeneracy, suggests that there should be a flat mass radius relation in this mass range, but actually these hot Jupiters are inflated, and that's a fundamental problem, and it's stood as a problem for close to 20 years, I think. The second thing I'll focus on is circulation and mixing. The best observed targets are these short period gas giant planets, and we infer that they have a very, very hot day side facing the star and a very cold night side. And mixing between those two regions is controlled by the dynamic flows in the atmosphere. And this is just a plot we'll see again later, where we have the phase of the orbit against the relative flux. And you see this observed black line with a gray uncertainty is this sort of curve. Now, the key is all these other lines are models. And you can see that even when they match the peak in emission coming from the day side, there's still problems at the minimum of emission on the night side. And we've been doing some work in that field. Finally, if I have time, I'll talk about some of our terrestrial work as well, focusing on moist convection. Okay, so let's move on then to the second layer of observations, the second layer of information. We have, beyond just the detection and the bulk properties, we have transmission spectroscopy, which allows us to work out potentially the composition of these atmospheres, just as the light passes through the atmosphere of the planet on its way to us as the planet is transiting in front of the star. So this is glancing incidence. The light is coming through a long optical path. So it's very sensitive to things like clouds or any sort of airborne opacity or gas phase opacities at the wavelength you're observing. We can also get direct emission from some of these transiting planets. Here's just an example of wavelength at the bottom against flux with the observational points. And in this case, there's model spectra that are trying to infer whether the atmosphere has a smoothly cooling temperature with increasing altitude, or whether it has an inversion like in Earth's stratosphere. We can go even further than that. Many of you will know Heather Knutson many years ago, and it's been done several times since, can observe the brightness of the system as the planet orbits the central star and reconstruct the brightness of the planet's photosphere as a function of longitude on the planet. So this plot here shows you that, in fact, this reconstruction done for HD 189733b is what's called the well-known hotspot offset. The substellar point should be in the center of this diagram, but actually the hottest part of the brightest part of the atmosphere in infrared is offset. Finally, using high resolution spectra, we can also infer winds. Ignaz Snellen, Matthias Brody, and Jamie Birkby and people have really pioneered this this technique. And there's only been a couple of results of wind speeds in the atmospheres of hot Jupiter planets, but that technique is improving, and with further instrumentation improvement, we'll get better at it. And the technique here is basically to use a forest of high resolution lines to then enable you to pick out the lines which are due to the planet's orbit. You can correct for the orbit and the rotation period, and the residual signature is the wind speed. Now, Tom Loudon and Peter Wheatley at Warwick in the UK also were able to perform this same technique at both ingress and egress to give us estimates of the wind speeds at different hemispheres on the day and night terminator. Very large uncertainties, but very promising for someone like me who's interested in 3D dynamics, that there are constraints coming. Okay, so that's the background of the observations. Now to talk a little bit more about my actual work and my group. So we're modelers, and we use a range of tools, but really our sort of racehorse tool is the 3D global circulation model, or general circulation model, that the Met Office use for their operational, as we would say, climate and weather prediction. And this is called the UM. I'm going to talk about the code a little bit, and then I'll talk about our results for gas giants. And as I said, if I have time, I'll talk a little bit about convection on terrestrial planets. The kind of stuff that we can do, you can watch the recording if you like and match these names to things you might be interested in. We have people working on paleoclimate, a little bit has just started on Mars, life climate interaction, etc. But the names in white are the areas that I'll focus on today. So as I mentioned, some work on the dynamics and the key problem of inflation, the 3D mixing, and then if we have time, convection. So what I think is unique about the way I work with the Met Office is we work in a shared development environment. So there's approximately 200 or 300 scientists at the Met Office constantly evolving a 1 million line program. It's a huge beast and it's moving very fast. And we committed very early to connecting with that. So we have to update our code every couple of months and lots of things change, which can be painful. But what it's done is enable us to feed back into the Mayne model, add flexibility, which has been vital for their development, and also pick out bugs. Just recently, through an intercomparison project, we realized that the entire model has had a slight offset in where the rate of transfer calculation was being calculated. And it was kind of not that important in a rapidly rotating planet with all the various processes included in the climate model. And we were able to highlight that in our work. So we have a connection through the model itself called the unified model. There's various other components that deal with the land surface, the rate of transfer, etc. But crucially, what we have is a shared code and also shared configurations. So anyone that comes into the collaboration can get a copy of the code and a setup, for example, for a basic TRAPPIST-1E or a basic HD-189. The process, if we move on to what the code sort of looks like in simple steps, it's a huge beast, but essentially it sets up a spatial domain. There are a couple of options for this. Deals with the advection, the flow in the atmosphere, calculates gas phase chemistry onto condensed phase, and then through to rate of transfer and loops around again. Now, the one thing that crucially that we've added is we've added the ability to create synthetic observables using exactly the same code that we use inside the GCM. So it's self-consistent. And we do that by cooling the rate of transfer at low resolution, because that's all you need to work out how the atmosphere evolves, but also again at high resolution to work out the spectral emission. My sort of drive here is to try to build a hierarchy in each of these boxes. So we have various gas phase chemistry schemes from very, very simple to more complicated. We have various condensed phase chemistry, condensed phase schemes from simple or complicated. Okay, so a bit about observations, a bit about the code structure. Now on to the actual science. So most of our work is focused on the most observationally constrained targets, of course, hot Jupiters. And one of the key things that I've tried to think about a lot in our group is the fact that we don't have direct spatial information. And these planets are very non-zonally symmetric. They have, as I mentioned, we think a day and a night side dichotomy, very hot day side, very cold night side. And yet when we observe them, we tend to either sum the whole of the terminator, which can be very different from equator, or maybe very different from sort of North Pole to South Pole, or we sum up the emission from an entire hemisphere. The phase curves, as I mentioned, where we look at the observation of emission over the orbit, give us some spatial information, but not as much, obviously, as I'd like as a theorist. So my job, or what I'm really interested in, is trying to see if there are signals in these observations where the dynamics and the 3D nature of the planet leaves its footprint, essentially. So there are three boxes here. We'll start with dynamics at the top, talk about chemistry in the middle, and the bottom box is for clouds, which I think we'll omit for today because that's kind of a deep topic in itself. Now, in terms of the dynamics, the way we solve the equations of motion in a global circulation model, usually most models use what's called the primitive equations. That's basically an assumption of vertical hydrostatic equilibrium and that the atmosphere is a thin layer. Now that usually works quite well for Earth. It's 6,000 kilometers of rock with maybe 100 or 200 kilometers of atmosphere on top. But perhaps for some of these exoplanets, that's less applicable. So what we have in the is uniquely the ability to actually switch between different levels of approximation to the dynamics, but use exactly the same numerical tool to really test these. So what we did, first of all, is, like many others, and the pioneer who sadly passed away recently, Adam Showman, really led the way in this field, was to look at the overall circulation for these targets. So this plot, you're going to see a lot of these. This is the latitude from the North Pole to the equator and the South Pole, and then pressure from deep in the atmosphere up to millibar, where we may see transmission spectra sort of dominates, to the top of the atmosphere. Now, the red is a prograde flow going with the rotation. And when we simulated this particular hot Jupiter 209 in 3D with radiative transfer, this was really the pinnacle of the sophistication used at that time. And we got an answer very similar to most of the other previous studies using perhaps more simple models. And that is a huge prograde super rotating jet. Some basic features of this planet are also at low pressures, you have a very short radiative timescale. The stellar heating is very strong. So you have a day-night dichotomy where you have a hot side and a cold side, as you can see in this plot of temperature as a function of latitude and longitude, and the arrows are the winds. As you move deeper in the atmosphere, the radiation timescale gets longer. The radiation essentially doesn't penetrate, and the advection begins to win. And actually you have a very symmetrical pattern. You have this jet and it smooths out the temperature differences between day and night. So this is all good and sort of makes sense. But if you go to a certain depth in the model, and this was actually predicted originally by Adam Schoeman and collaborators, that around about where the photosphere is, you actually have this offset that I mentioned. So here's the substellar point at 180 degrees. But the hottest and therefore brightest part of the infrared is actually shifted to the right. A simple way of explaining this is the wind is moving the heat, but it's not quite like that actually. The structure is dominated by wave processes, which in a simulation are set up very, very quickly. They're very fast acoustic waves, and then that shapes the dynamics after that. But essentially it's the same outcome, that the radiative forcing mixed with the dynamic and the pressures ends up with this shifted hotspot, just like we observe in the hot Jupiters. So moving on, we then tested these dynamical equations because naively several years ago, I thought, well, the atmosphere of a hot Jupiter is very, very deep. Not only that, Jupiter has a deep atmosphere, but the radiation only penetrates to maybe a bar. Here we have a deep atmosphere that's been driven by radiation over very large pressure ranges. So we tried to use the different approximations, and here's just the horrible equation for the zonal velocity that some of you may know. This is just the wind in the longitude direction, the zonal wind speed. This is what's called the material derivative. But the key parts here are these terms where we have the very simple equations that assume a thin layer, and primitive equations they're called. And you can see you just assume the radius of the planet, not the actual radial position of your fluid parcel. And you also lose this term entirely, and you lose this Coriolis term here. So we tested the difference between those, and naively, as I say, I expected it to make a difference because the atmosphere is deep. But actually, it turns out, disappointingly, it made very different distance, very little difference, which I now understand. So these are the same plots you saw just previously. This is for a very simplified equations of motion, and then slowly as we step through to the more complete. And you can see to the naked eye, they're pretty much the same. There are some differences, the breadth and latitude of the jet and the strength, but really these are very similar structures. And on reflection, we realized that although the atmosphere is deep, the radius of the planet is so huge that it's still effectively a thin layer. So actually the primitive equations are a fairly good approximation for these simulated results of a hot Jupiter. That got myself, Pierre Murier, Florian Debras thinking a bit more, and we worked a little bit more to see what more we could understand. And actually we moved on to extended atmosphere mini Neptunes or warm Neptunes. So I just mentioned that the thin fluid atmosphere is kind of okay for a hot Jupiter, because although the atmosphere extended, the size of the atmosphere here, Z atmosphere, divided by the radius of the planet is a very small, it's 10% or less. But if we move to a warm Neptune that has an extended atmosphere, the radius is smaller and it can actually get much higher to about 20%. So really very, very simple analysis that we performed was just standard in climate science to look at the size of these terms that you're emitting and compare them, and just came up with this classic expression of where the thin fluid approximation and the associated approximations would break down. Simply when your vertical velocities here denoted by W, if they become significant compared to the latitudinal flow times by some tangential tangent of the latitude itself, then these equations start to break down. So doing some sort of algorithmic sort of or manipulation of the equations, we had estimates for these two terms, the vertical velocity and the latitudinal velocity. And that showed us that warm Neptunes were in the ballpark or in the region where we expect these equations to break down. So we performed some simulations, same plot as before, a slightly different color scale, just because I realized I'm colorblind and the other color scale was very difficult for me. So we changed color scale halfway through the papers we were writing. Now here on the left, so again, you have latitude against pressure. So on the left, we have simulations performed with the primitive equations. And on the right, we have simulations performed with the full equations. Now you can see the top two and the middle two panels are different and quite significantly different. And what's happening here is the top panels are the simple setup for a warm Neptune, but we've enabled or reduced the difference by rotating the simulation faster. Still different, but we've rotated the simulation faster and it started to remove that difference slightly. And you can just see that simply because omega appears in this term here, which then goes into the balance between the two terms. Finally, we did a test where we just increased the radius of the planet significantly, so it effectively became a hot Jupiter, and then we have a very similar setup here, a very similar result rather. So the key conclusion is just that the atmospheres of these planets, these are just simulations, they're not meant to be physically complete or accurate, but it's showing you that for probably the next very important set of targets, warm Neptunes with extended atmospheres or perhaps even super Earths with extended atmospheres, we need to be careful about the dynamical approximations we make. One other thing, as I mentioned, we were interested in that's a dynamical process potentially is this inflation or this larger radii of hot Jupiters. Now, there's various ways you could solve this. You have tidal interactions, maybe the tidal heating is inflating. That's still on the table, that could still work. But if you have a significant enough Q or a significant enough sort of frictional effect, then that also has a shorter timescale. So you might expect that to not last very long, essentially. And we think that these planets are locked and circularized very quickly. There's potentially magnetic effects. There's ohmic heating in the deep atmosphere. That's still potentially possible. But one of the intriguing things was actually put forward by Tristan Guillot and Adam Schoeman, which is a sort of dynamical mechanism. And they argued that, say, a few percent of the kinetic energy that was, or the energy rather, from the irradiation, if that was pushed down through the radiative region to the convective region interior, then actually it can be circulated and inflate the planet. Now, we noticed we were running simulations of these planets, and when you run a 3D GCM, you initialize your simulation with a temperature pressure profile. So here's an example of temperature against pressure. There's a blue night side here, and then there's the sort of mid profile in the middle, and then a hot day side. And really the radiative transfer that you use to start this temperature pressure profile doesn't have much impact down here. This region is radiatively inactive. There's no radiation getting to that region. So really your initial state is frozen in. So that initial state in the deeper regions is important to setting the global radius of the planet. So whatever happens down there in our simulations is dynamic. So working very closely with Pascal Tremblon, who really led this work, we looked initially at the simulations we'd run for a hot Jupiter and observed that in these temperature pressure profiles at different longitude, actually the deep atmosphere was starting to heat up. This kink here is where the initial condition is heated slowly and it's coming from above. And as the simulation moves on, this sort of heats and heats and heats and heats. And that can't be radiative because the radiative transfer simply doesn't have an impact down there. So it's a dynamical effect. So Pascal, Gilles, and a few others, we worked together and created a 2D steady state solution. And we used boundary conditions from the 3D model to decide where the flow, the balance between the vertical and the horizontal. That's what this expression here is. In order to have the 2D equation, you need to know what your boundary conditions are in terms of the flow vertically and horizontally. So this gave us this kind of alpha value, which we took from the 3D solutions, put into a steady state 2D model, and the temperature pressure profiles which came out were actually much hotter. These steady state solutions were much, much hotter indeed. And in fact, hotter even than the convective, the adiabat that you'd expect the atmosphere to alight or rest on deeper in the atmosphere. So this is caused by the advection of high entropy, or in climate science we'd say potential temperature, which is being driven down into the atmosphere and altering this internal region. So that was interesting. It's a 2D model. There was boundary conditions and assumptions, etc. So we tried to look a little bit more detail, working with Felix Sainsbury Martinez and the dynamical core from LMD. And we actually saw this plot on the left here. So the Dynamico was run for tens of thousands of rotation periods. We have pressure against temperature, and you can see the initial profile, and then this is the evolution of the profile onto this hotter adiabat. Now, this was done without proper radiative transfer, but using my own model, we also run the same with radiative transfer, but we couldn't achieve quite the same length of elapsed time, but the evolution was similar, and we sort of got about partway through this diagram, and we're working on pushing that further. So this potential temperature flow is sort of visualized in this stream function plot, just showing you where stuff is flowing. And what you see is latitude against pressure again. And these red and blue are just showing you that there are cells which are actually driving material. I'm going the wrong way, sorry. They're driving material down, high entropy material down into the deep atmosphere, which is causing this change in the adiabat. The problem with these simulations is they have a brick wall or a solid boundary here. Now, below this boundary, we expect convection to be happening. But here we just have a single isotropic temperature that's emitting and a solid reflective boundary. So although this is really promising and super interesting, and I think maybe a solution to the radius inflation, we really need to deal with this this inner boundary issue if we are to be certain and if we're to fully quantify the effect. So I've just actually had a project funded for the next 4 to 7 years, where we'll be using the next generation climate tool called ELFRIC, where the goal is to couple this to an internal anelastic model of the convection. Now, we need the next generation tool simply because it scales much more efficiently. It's designed for exascale computing, so it can match the scalability of some of the codes like MAGIC or ASH. So we'll be attempting to couple these two across. It's a hard job, I realize, so that we can observe how the convection interacts with this large scale circulation and potentially look at the radius inflation, of course, but there are lots of other exciting things I think we can look at. So that's a little bit about the dynamics. Secondly, the second sort of topic is to talk about how the dynamics impacts the observations. So the first topic was how the dynamics might impact the broad scale properties, i.e. the radius of hot Jupiters or the radii. But now we're looking at the observations themselves, like emission and transmission. And for that, we need to include some chemistry. So we also built a hierarchy of chemistry models, going from a very simple Gibbs minimization equilibrium scheme to a simple, what we call a relaxation scheme, where you can look at interconversion between two species, for example. And finally, a fully kinetic scheme where we use the work of Olivier Venot and we use the reduced networks and put them in the 3D model. And we're going to use that to observe these potential discrepancies between the observations of the emission as a function of orbital period. So to introduce the topic, many of you will be familiar with this, I expect. This is just a plot of mole fraction, or the amount of stuff versus the pressure in an atmosphere. This is done in 1D. And the lines that you see are equilibrium calculations, equilibrium calculations or non-equilibrium, the dashed and the solid. The non-equilibrium calculations include vertical mixing in the atmosphere and photochemistry. Now, what you can see is in the top of the atmosphere, there's regions where photochemistry really diverges your mole fractions and is having an effect. But this is at very low pressures. This is in bar, so 10 to the minus 4 bar. We then have a region where we're very mixing dominated. Now, this leads to this concept of quenching, where the vertical mixing here is freezing in the abundance at this level. You have material at this temperature and pressure and is being mixed upwards, and the chemistry isn't fast enough to revert it back to chemical equilibrium. It's a very well understood mechanism. It was observed or inferred in Jupiter's atmospheres in the late 70s. And then as we go deeper, the temperature and pressures are higher and the chemical reaction speeds are faster. So everything down here is basically in equilibrium. So we have an equilibrium region, a sort of mixing dominated region, and eventually a photochemistry dominated region for a hot Jupiter. So the accusation was from previous work that this discrepancy from the observed emission as a function of orbit, so this is the day side of a hot Jupiter, this is the night side, and the discrepancy between these models was perhaps evidence that material was being mixed between the day and night side. Here, we don't just have vertical mixing, we have a day and night side with flow between them. So it could be that this same quenching would be happening horizontally too. Now, again, Adam Showman led the way with Curtis Cooper, showing a very simple model in 3D to test this, but they actually found that the vertical mixing was dominant, but they had a very simplified chemistry scheme, very simplified radiative transfer scheme. Marcelo Agundes, working with Eric Hebrard and others, did a much more sophisticated chemistry, but a more simple dynamical model in sort of pseudo 2D. And they actually found that the horizontal mixing was more dominant. So we decided to test this by performing 3D simulations with sophisticated chemistry and radiative transfer as well. And this was recently followed up by João Mendonça with the Thor model. So what we've done is to simulate actually now a range of hot Jupiters, and there'll be a paper submitted soon on other aspects. The 3 papers that we've focused on so far have been on HD 209 and HD 189, as they were more looking at mechanisms. And now we're working on a follow-up looking at a much larger range of planets. But these are just some simulations from our state-of-the-art model. So it's got full radiative transfer in the terms of a GCM, the most sort of sophisticated level you would find. It has gas phase chemistry. And on the left, we have plots which are equilibrium, and it's showing the methane mole fraction. And on the right, we have the chemical kinetics, where your flow is allowed to shift the abundances and move them around, and the chemistry competes with that. So this is longitude against latitude. So here you can see, as you might guess, you have a hot side and a cold side, and the methane abundance follows suit. As we turn on the chemical kinetics, actually at this pressure level, which is high in the atmosphere, this is millibar level, you have a very, very different methane distribution. So what we did is to put some tracer particles into the atmosphere to try to determine what was dominating the mixing. So the plot on the left shows you the latitude again, South Pole to North Pole, and pressure. Now this box is where we initialized some tracer particles. So we started some particles in here and gave them a value, and then allowed that value to decay over time. And this allowed us to determine that material was pulled in latitudinally into the jet region at the equator, mixed zonally around the planet by the jet, and also vertically here. Now this used to be a movie, but it failed so many times I gave up on it. So now it's just a boring figure. But the key is to see that material is moved into the jet latitudinally. It's then mixed vertically and zonally around the planet. And that gives you your final mole fraction of methane in the upper atmosphere. So here's some plots of the mole fraction just at the equator at different longitude points around the planet for HD 189 and HD 209. The dashed lines are the equilibrium calculations. So again, you have this hot side and cold side dichotomy. You have the difference in the methane between the two, and the same in 209, although the structure is slightly different. But crucially, what you see in the kinetics in the solid line is that at some point in the atmosphere, if we focus on 209, the material is fixed, and then it's actually mixed in this region zonally and sort of between the poles meridionally and also around the planet. And at some point, it's then mixed vertically. Why does that matter? Well, what that means is the abundance of methane that you are observing at millibar is actually set by the conditions and the three-dimensional flow deeper in the atmosphere. And the point and behavior of this interaction between chemistry and dynamics changes for different planets. As you can see, the 189 is different to 209. So these are very sophisticated simulations, and that's great. But what they're doing at the moment is exposing a mechanism. What we need now is a lot more work to quantify it, to say, can we observe the methane abundances in the upper atmosphere and use that to infer the behavior of the three-dimensional mixing in the deeper atmosphere? But what it is saying is that if you use retrieval techniques to determine an abundance in the upper atmosphere, you need to be very careful with the assumption of equilibrium, because we're indicating here that that assumption should not hold. And this is work by Ben Drummond, which you can see in sort of recent slew of papers. And as I say, we're now following this up with many more planets. In these papers, we also created simulated observables, so going beyond just the mechanism, but also trying to see, could we observe it? So here we have wavelength against a radius for transmission spectrum using JWST, and you can see that the red line, which is the sort of chemical kinetics, the simplified version in this case, and the blue line, which is equilibrium, we have very different signatures here due to the abundance of the non-equilibrium abundances. So we think this is detectable. We also did the same thing for aerial, and here we zoom in on a particular region. This is, in this case, this is emission, and we see this difference. These are both JWST, sorry, but we also did the same calculations for aerial. So emission and transmission should be able to detect this. I won't talk about clouds too much today because there's a lot of work we've done on it and others too, but just to say that we've also got a hierarchy of cloud models. So we use Christian Helling's microphysical high temperature cloud formation model, which does everything from nucleation of grains, heterogeneous condensation and evaporation onto the grains. And we've coupled that in 3D and did some studies with that. We also coupled the very famous Ackerman and Marley Eddy-Sed model, which is a steady state model, which basically highly parameterized and sort of assumes based on condensation and some input parameters what the structure of the cloud is. And we've turned the radiative transfer impact on and off. And all I want to say from all of that work is that it's clear that the radiative impact in clouds, if it wasn't obvious from thinking about how clouds work anyway, the radiative impact of clouds is very important. So running simulations and then including clouds afterwards is useful as a part of the tool, but it is missing a key element, and that's the interaction of the radiative transfer. Okay, so where are we? So in the final sort of 5 or so minutes, I wanted to talk a little bit about another arm of what we do, which is terrestrial planets. Just to summarize, sorry, so we spoke here about the dynamics and how the advection of potential temperature could lead to a mechanism to explain inflation. And also spoke about how the 3D mixing is setting the abundances of various molecules in the upper atmosphere. So now if we move terrestrial planets, we've been working mostly the LMD model in, well, there are several models that are being applied to terrestrial exoplanets, and each of them have their strengths and weaknesses. The LMD model, for example, is particularly flexible and very good at looking at the ranges of composition. And our model is designed to be sort of much more accurate for Earth. So we've focused more on Earth-like compositions, but trying to explore whether the parameterizations and the treatments that we use for Earth could in fact work for other planets. So just to start off with an introduction, you're probably all very aware, but we found lots and lots of Earth-like planets, with TRAPPIST and Proxima being the most sort of famous ones. I think we're all aware that the activity and flares from M dwarfs is an important thing to take account on. Lots of people working on that. There's recent work by Eric Wolf and collaborators using the Wacom model, which is really great, and we're following that up at the moment. But what we've concentrated on is clouds and convection. We know in Earth's climate that clouds and convection are the leading cause of uncertainty, also huge drivers in the overall average climatic state. So we've tried to understand how good is our treatment of clouds and convection in these atmospheres of these distant planets, and indeed, what can we infer from observations? So we would call that a process study, I guess, in climate speak, where we try to just focus in on individual processes. So we did some work on Proxima Centauri, very, very simple stuff. We just took an Earth-like atmosphere, some nitrogen, some moisture, some CO2, and we put it in the orbital parameters around Proxima Centauri, the star. And we did a sort of 3-2 resonance, which is allowed by the observations. And then we did this sort of tidally-locked simulation as well. Now, the key result from that, which I think was something that was sort of obvious on reflection, but I think the field hadn't really taken to grasp on, is that for these tidally-locked planets, you essentially have a huge convective region, if there's moisture in your atmosphere, that's completely dominated over the substellar point. Now, that has massive implications for your moisture cycle and your clouds, that all of the moisture here is sort of contained, all the convection, all the cloud activity is contained, and then it's sort of moved around the planet. Again, like hot Jupiter's, it's a balance between this advection and the sort of heating. So this plot, sorry, just shows the various cloud structures. And these are some examples of the rain, the surface precipitation. So you can see that it, in this case, where we've assumed an Earth-like atmosphere, so it's a very simple assumption, all of the rain is dominated. So you can imagine if you had a desert here, this planet would become desiccated completely. Whereas if you had an ocean that was able to recirculate, then you might be able to keep it moist. The other thing we were able to show is that actually the surface conditions, so we're not going to be able to see the surface of these planets in the near future or midterm future or even long future, but what we're trying to do is, can we use the large scale climate to infer what the conditions are like? So whether water is present depends on the location of climates and the interaction, the location of continents and oceans and the interaction with the circulation. So we also did a study where, after we realized that the entire sort of hydrological cycle is constrained to this hotspot, this substellar point, we did the same simulation, but we changed what was under the hotspot effectively. So these are just plots of an aquaplanet here, and then with a continent put underneath the hotspot, and they show you the wind and the temperature at different levels. This is the surface, or very close to the surface. Now, as we go up into the atmosphere, you can see that these wind structures and temperatures between these two models are different. Now, these models are exactly the same, but the difference is one has a continent under the hotspot and one has an ocean. And if we go even higher, where we might start to perhaps get transmission spectra eventually, then again, we see different structures and different circulations of the moisture and cloud. So that gives us some hope that we might be able to infer more information from more detailed observations. But obviously, this is a future goal. The final thing we've been really focused on, as I mentioned, is convection. So what's super interesting about tidally locked, potentially habitable Earth-like planets is the simplicity of their kind of heat engine. In a sense, you have a day side here where you have radiation coming in and then long wave radiation, which is cooling. You have a night side, which is only cooling. So all of the heat and moisture that gets to the night side has to be transported from the day side. Now, crucially, in an Earth-like planet, you have a surface with convection that drives heat and moisture up, and then flows that convert or transport rather that heat and moisture to the night side. Now, this side is absolutely key because it's your thermostat. The water and moisture and heat transported to this side of the planet control the cooling. So you have your heat pouring in and you have your sort of valve coming out. And what's controlling that is the moisture and heat being transported across. So you can see very quickly that convection here at the substellar point is vital to that understanding, and it controls the global climate. The big Q is kind of heat, and then the little q is sort of what we just use for moisture. Now, what we know is that convection in simulations is parameterized. Now, you can parameterize it very well for Earth because we can observe how high the troposphere is and things like this. So we know very well what the convection works like, and we have various ranges of simplicity and complexity in the convection parameterizations. But how does that work for a terrestrial planet orbiting an M dwarf, where the M dwarf spectra is different? There'll be more absorption in the atmosphere, for example, as opposed to all of the radiation hitting the surface. So what we did is these are big global simulations, and we actually zoomed in and used what's called a nested suite. So inside this box, within the global simulation, we performed a very high resolution convection permitting simulation. And this is the different fields. So we have the surface temperature, the sort of precipitation flux, is the rain minus the evaporation, and the upward air. And these plots on the left are just the ones from the global model, as if when we run it without the high resolution. And these are the ones from the global model when we include this high resolution mesh over a region. Now, what you can see is that largely the structures look fairly similar between the surface winds and the temperature. They're not that different. And the total precipitation flux doesn't look that different. I mean, this is very well resolved, but it's fairly different, fairly similar, sorry. And the same with the upward velocity. So that gave us some comfort that these convection parameterizations were actually giving us reasonable answers compared to when we just resolve it as a physical process directly with the equations of motion. The problem is that with computational limitations, this was as big as the box we could get. And really, it may well still be being driven by the sort of impact of the lower resolution simulations around the outside. So there's more work to do here. But just to show you a super cool picture, this is the regional model and the global model where we show cloud cover. So this is what you get in the global, and then this is what you actually get with the high resolution. So in order to try to determine what happens, of course, what we'd like, and I'll talk about it briefly in a second, is a model that can do the whole globe, that can resolve convection everywhere. But we don't have that. So we tried to measure what we thought we created a measure of the horizontal transport of moisture, the vertical transport of moisture and heat, and the day-night difference when you have the nested region with high resolution simulations, and you have the global simulation with parameterized convection. And what we found, all these different simulations are kind of little simulations with different perturbations, etc. And we found that actually the global simulations all have a fairly similar level of day-night heat redistribution. Now, when we do the high resolution estimate, what we found is actually in that region, there was a very different vertical transport. Although the plots look very similar, just morphologically, actually the heat transport was very different. So that allowed us to infer that there may well be a different horizontal distribution. So just to be clear, we can only measure a different vertical distribution in the high res because the high res only has a small area. So we then have to infer the horizontal. So what's this telling us? It's basically telling us that we need to be careful about our many parameterized schemes we use in these 3D GCMs for Earth-like planets. And we need to explore, again, some form of ground truth, which in this case is a convection permitting simulation, their performance. Now that brings me back to our sort of recently funded project, the second arm of this ELFRIC project. ELFRIC's key motivator, the Met Office in the UK, wants to create it in order to create global convection permitting simulations of Earth. So we want to do exactly the same thing for an exoplanet. So we're no longer limited by this box size. But crucially, we can do this not like a large eddy model, but we can actually do this with including other important physics like the chemistry, the radiative transfer, etc. And that's work that's kind of ongoing. I mentioned earlier that people were working on flares, etc. That works. Some of it's been published, the precursors, but more of it will appear soon. Okay, so just to summarize that last part, that the treatment of convection and the clouds that the convection causes is critical to the overall climate. And we've performed resolved convection simulations to show us that we need to use care when we apply these simulations. So it's a bit of a broad set. We've gone from kinetic chemistry of methane and carbon monoxide across to sort of rain clouds and moist chemistry. But hopefully that's given you a flavor of the kind of things that we've been doing at Exeter. We've got some really good model hierarchy stuff now with self-consistent observations. We can study gas giants and terrestrial planets. And I hope that I've shown you some indications that working with Pascal Tremblon and others, that there's possibly a dynamical solution for the radius inflation, and that actually the 3D dynamics really play a key role in the observations of hot Jupiters, and that convection is something that needs to be thought about carefully. So the future, as I said, is to use this new model. I had funding permitting in here, but I recently got the funding, so I need to delete that sentence. So that project will start in February, and it's completely open source. So anyone that's interested in doing GCM simulations, in the next 6 months or so, we should have our working model completely open source, which people will be able to download and use. Okay, thank you very much for your time. Thank you.
Thank you very much, Nathan. So are there any questions in the audience? You can raise your hand or take the floor if you have any questions.
I have a question. Oh, sorry.
Yeah, please, Alain.
I have a question, Pierre Donsard speaking. It's about the dynamics, the first part of your presentation. As you probably know, with the Jupiter observations by Juno, there was observations that the depth of the circulation is between deep and shallow. And one reason invoked is probably the hydrogen electrical conductivity, and that was one of the last work of Adam Sharman, showing that the resistivity of the even molecular hydrogen can be high enough to influence the circulation. And this is really something very new in circulation models. Is there some possibility to extrapolate that to Jupiter and other planets? And are you thinking to include such resistivity factors in your equations?
Yeah, exactly. So obviously hot Jupiters are very strongly radiative forced in the upper atmosphere. So it is sort of slightly different, but you're right. At some point, we transfer from a stratified region to a convective region, and you'll have a change in conditions as you go through those. So yes, indeed, I want to do that. And that's why I want to incorporate these anelastic models, which have at their heart a really good understanding of those types of issues. Now, the critical and the difficult part, of course, is how I deal with the overlap, where I move from the models like MAGIC or ASH that do a very good job of the sort of MHD, essentially, in the deeper atmosphere, and then how I move through to the GCM, which is not MHD, it's just the hydrodynamical model. And what I'll be doing is very much following the footsteps of Adam to use parameterizations in that overlap region. So I have some flow of heat and possibly flux of material, but then use parameterizations that we can exactly follow from Adam to use how that moves into the hydrodynamical region, parameterizations of the drag, conductivity, etc. So yeah, absolutely a lot of work to do.
Thank you.
Thank you.
Alain, you had a questions. You had a question.
Yes, thank you very much for this very interesting presentation. I have a question regarding the upper atmosphere. You know that we observed 70 years ago, the first detection of atmosphere was about the evaporation. And since then, we observed many cases of evaporation and hydrodynamical escape of exoplanet atmosphere. And I wonder if your model is able to explain this, or at least to produce some kind of constraints where the hydrodynamical escape start from in the point where from the altitude point or also longitude altitude point. Your 3D might be interesting to know the process involved and the place where this process takes place.
Yeah, a good question and a really important point. I agree. Sadly, I think with the current incarnation of my model, we would have little useful to say. Now, the reason is that we might be able to extend our upper atmosphere to lower pressures, put in some chemistry, and maybe use some very parameterized treatments of where the hydrodynamical escape will kick in, etc. But really, our model is ill-suited at the moment to deal with particularly the photochemical effects and the photolysis, etc., that might happen in the upper atmosphere regions, especially where the flow becomes kinetic, essentially, instead of kind of more fluid. So I think the short answer is we won't be exceedingly useful. Tommy Koskinen and others are adapting higher atmosphere models to look at those kind of problems. So it's something we could look at in a very highly parameterized way, but I don't think we'd be over useful for those types of issues.
Thank you.
Are there other questions?
I have one. That's not really my topic, but that's interesting. This motion in the atmospheres. So there's one point I probably misunderstood in the end. You put a crazy high resolution in the zoom-in region to try to capture the convection. So what does it mean when you don't have this resolution? The convection is not captured ab initio, but you try to model it in kind of subgrid fashion?
Yeah, exactly. Sorry if I wasn't clear on that. So, you know, similar to sort of mixing length theory that you might use in a 1D model, when you're not resolving the convection, you use a parameterized scheme, a subgrid scheme. There's a whole host of those available for Earth climates, from the very simple ones, which essentially relax you onto an adiabatic, a moist adiabatic profile, to much more sophisticated, what are called mass entrainment schemes, which try at least to do a better job of where materials entrained and detrained. So what we did in that paper, actually, by Denis Sergeyev, is use a range of different parameterizations, from sort of super sophisticated, which is great, lots of physics in it, but it's all tuned to Earth, or very simple, which misses loads of physics, but at least is more flexible, and compare those to the convection simulations themselves, where we hope we're kind of directly modeling exactly what convection would do. And we had one of those answers, which is interestingly publishable, which is using these schemes is probably not too bad. So lots of GCM people were happy, but then we did show some quite important differences. So lots of other GCM people were quite happy too. So it was one of those kind of papers.
Okay. So sorry, just to continue. You mentioned you are using the LMD Z code. Or is that Dynamico? Because I know this code is developed by your colleagues at Institut Pierre-Simon Laplace nearby.
Yeah, so that
studies, but they have these two different codes. They have the LMD and the Dynamico, which is the new version.
Yeah, so I haven't used the main LMD model, the LMD Z, I think it's called, or LMD generic. So I haven't used that. I've been involved a lot with comparisons with Francois and Thomas Fauché and Martin Turbre, but I haven't used that. But what we did use for the hot Jupiter deep atmosphere problem, through Felix Sainsbury Martinez, we used Dynamico because of its extreme scalability. So we could run that model because the deep atmosphere evolves so slowly. We needed a model that was capable of running for a long time scale very quickly, and Dynamico can do that. So it has less physics in it. The rate of transfer is a bit more simple and stuff, but it can run quick. So those results where I showed the evolution of temperature pressure profile, they were from the Dynamico model. Yeah.
Okay. Thank you.
Somebody else? Maybe I have one question on my side. Are there some interesting ways to compare your models, your simulation with the solar system planets? You mainly talk about hot Jupiter, so which are not present in the solar system, but still, are there ways to compare with our planets?
Yeah. You won't be surprised that I've been asked that question many times before. And the thing is, once you have a tool like we've developed, there's so many things you can do, and there's never enough people. So, so we do have ambitions of studying solar system planets, and I have initiated that. So we've just recently started a student working on Mars, and we've also started someone looking at Jupiter. But I wanted to sort of jump to exoplanets first, get an idealized, very flexible model working to start to look at broad mechanisms, which is really the thing I really am interested in, and then start to fill in the gaps, I guess. But I need, it's just too much for me. So I need, as more people are joining Exeter, we have someone called Steve Thompson, who's just been hired as a lecturer. He's an expert on Jupiter as well. So I'm hoping that he'll carry that. Now, of course, the new project I described, where we're coupling a convective interior model to an atmosphere model, I think that has absolutely amazing application potential to Jupiter. And I think it's one of the reasons that project got funded, but I don't yet have the expertise to do that. So I'm looking for collaborators, and especially because the code is open source. Once that's ready, I hope through collaborators, we'll be able to impact on the Jupiter studies as well.
Okay, thank you. I see no other questions. Are there? No, so maybe we can stop here. Johan, Sandrine,
Yeah.
close the session.
Yeah, so just in case, I will at least stop the